working in Stitch Fix in Amazon, right? Before co-founding Marqo, and I believe you're calling from Australia, right? Yeah, so pretty early your time. But yeah, you could talk about multimodal vector search and kind of see how to use the open source library Marqo to enable that. So yeah, for the audience, feel free to send your question on the chat, and the speakers can answer them asynchronously. And then we'll also have a sort of 5 to 10 minutes short Q&A session towards the end after both speakers has finished with the presentation. So with that, good luck to have Adrish. If you can start sharing the screen, just slide, and then get started with the talk.
Can you see my screen?
Yep, I see it.
Okay, very good. My name is Adrish Sannyasi, as James mentioned. And first of all, thank you for inviting me. My background is not research. My background mostly in the sales and customer engineering side. That means I work with customers to enable and implement a lot of this data and ML infrastructure. I also have a lot of this biomedical background because I work with a lot of healthcare customer, and I have learned one number of things over the years. But also I'm learning this space, as this space is new for all of us. This is something, it's a summary of the things that I'm learning. It's not like I'm an expert in the field and I'm working for the last 10 years on this, but this is basically a summarization of the things I'm learning, and obviously we'll be learning together as things are changing almost every day. So with that, the stuff that I want to present is 3 buckets. One is that we're going to talk about the use cases, the motivations behind multimodal AI in healthcare. And then second is there are some changes happened post LM, like how multimodal medical AI is getting developed. This concept of multimodal is not new, but how it is approached post GPT-4 is really different than what we used to do before. So I'll describe a little bit of the recipe that I've seen in the recent papers, and some of the thought process behind how this field is moving towards much more interactive AI. And the third is I thought it would be useful to discuss some of the nuances of medical data and some of the challenges we might face in validating and verification of any AI, including multimodal AI. Okay. So let's talk about a little bit about the use case to motivate the conversation. If you think about the amount of data you were talking about here, the single hospitalization can have close to 150,000 pieces of attributes, and those data sets could codify a lot of knowledge that is gathered over time. Because you think about places like Kaiser or Stanford, people are prescribing medications, they're doing surgery and doing various kinds of procedures. You can actually learn what people are doing just looking at the data. And that's one of the biggest advantage right now we have in analyzing records. Previously, 10 years ago, this data was a paper record. So it's no way to do this kind of analysis that we could do possibly today. And we have data beyond hospitalization, like it could be data from your Fitbit device, Apple device, or could be social data that might be useful. So this is just one piece of information, but the variety of other things might be in the picture for healthcare. And if you think about it, medicine is by definition is multimodal, because when you go to your doctor doesn't just look at your lab test. They have a conversation with you. They probably look at how you're talking, whether you're balanced, and then also they look at your images, and maybe they look at your skin, like a photo of your skin. So by design, this healthcare itself is multimodal. That's why this multimodal architecture is so attractive for healthcare, because they emulate the conditions that clinicians and the patient go through every day for their complex decision-making process. Furthermore, there are some research done even before ChatGPT that in most of the domains, most of the AI models, the performance of the models could be significantly improved if you close to 10 to 30% improvement is possible if you use data from multiple modalities. And the second thing that happens when you use multimodal data, you can avoid a lot of error and biases if you have data from multiple places. I'm going to explain a little bit more on that when I talk about the data in general. So emergence of LLM now provided a significant opportunity to redefine and reframe this conversation. And there are many things that LLM could do, but I thought there are two things that LLM really going to be changing the healthcare AI landscape. One is this generalizability. So I worked in a lot of healthcare models development work. What we used to do is we develop a lot of this task-specific models, like a risk prediction for diabetes. Or even for the NLP task, what we used to do is very specific things like, extract things which are related to, pancreatic cancer. So it's that every time you have to use a new task, you have to develop almost a new model by going through the model development process, like, collecting data, going through the labeling, and then going through the supervised modeling process and evaluation. So so the pace of development and implementation was really slow. So one of the things that large language model architecture provides is a generalizability. So I've done many experiments, and a lot of people have done these experiments over time, over the last 6 months, is that just using prompting and in fine tuning, you can you can use this LLM for multiple different tasks, which is very powerful and saves a lot of cost and money for deployment of the system. And the second thing that is really important here is the interactivity. So before, let's say I develop a predictive model and it's a risk score. And there's no way for me to now interact with the system and say, what about this? Why you are saying, risk is high? So I cannot have this kind of conversation. So what LLM aligned AI provides is to have this kind of interactions. And, I can have interaction with a patient about the score, or I can have a interaction with the clinician so that I can clarify things, which is what actually clinician or a patient wants, not just a number, but how can I understand this number better? I think the natural capability of LLM is to have this kind of interaction, and which provides a significant opportunity for various kinds of use case. So what's the overall vision? So overall vision is to think about is actually have a medical assistant. So medical assistant could be two things. One is for us, like as a consumer, that I can ask a question about my symptoms and get the results back. Instead of asking questions to Google, you can ask questions to a much more clinically aligned chatbot or voice bot so that I can get my answer back. And the second one is clinicians, that clinician should be able to have a conversation with this agent. And then this agent should be able to automate a lot of the tasks for me so that I don't have to do a lot of the administrative activity. And also it should be able to predict my health conditions, like whether I'm going to have a heart attack or not. It should be able to tell me all those things. And behind the scene, this agent is going to have a couple of interesting things. First is it should have access to my electronic medical record, and that's where the privacy, etc., comes into picture. But it is possible to access those things in a secure way. And then this agent will also have access to large set of medical knowledge in books, journals, or articles, or knowledge graphs. so that as a clinician, as a patient, I don't have to go through hundreds of journals and hundreds of books. This will give me answer, and that's something proven already, that LLMs have a significantly good job in reading things and summarizing, and giving the results back. So I think this is the overall vision. So now, how do you realize this vision? And this is some of the examples of that. This is an example of a decision support system that says, let's say it's a insulin required is one of the trigger or alert, but then clinician can ask, why you're saying it. So that's the concept of interactivity. And think about this is a combination of text and a voice that would be important in terms of the context of the application. The second example is where LLM should be able to create a radiology reports, but they should be able to create that in a much more visualized fashion. For example, it writes a report, but then it points back to the image about where it sees anomalies or abnormalities. And then this agent then could have a conversation with the clinician. So if you think about, we are having image, text, voice, all interleaved together into this application. And that's where the vision of the future is for, let's say, for radiologist workflow. And then lastly, this is for this example is for a surgical scenario where, let's say, is a continuous video of surgery is getting taken, and then this is a bot is going to look at the anomalies in the video streams and is going to suggest things or have some conversation with the clinician, help the surgeon with a better improve their surgical procedures. So these are the examples I've given. These are all examples of interactivity between text, image, and video data, and you can easily see that why multimodal AI would be a default, because there's no reason to not to have this kind of interactivity. Why you go for less, right? So now there's a couple of other examples that I have, like a clinical documentation. When you have a conversation, speech to text model could convert those conversation into clinical documentation, and then clinical documentation could have access to a structured or unstructured data, images behind the scene, and it provides a collaboration with the clinician to complete your documents. And then, of course, a patient assistant chatbot that I already mentioned. It could be a symptom checker or coach, and so on. So now let's talk about what's the best way to some of the ways to create this, create this multimodal AI. And there are, I think this is actually changing a lot, as I mentioned. And what I'm showing you here is some of the things that I've seen in the latest research paper from Harvard and Google and other places, the way they're approaching this problem. But there's a variety of ways to approach it. But one of the common ways I've seen is what I'm going to describe here. So general recipe is to align multimodal with the concept of LLM. That means I have a foundation model. It could be a foundation model for generalized foundation model, let's say like GPT-4 or PaLM and Flamingo and others, where I have either a text model or the vision model or maybe a multimodal foundation model. And then I take that, I don't have to start from the scratch, and take something which is already available because it has already data from the web, and it does a reasonable thing. Like GPT-4 is actually very good at medical related use cases already. So, I should take advantage of that rather than try to build everything myself. And then I apply there, take the medical data from, structured data, unstructured data, videos, and images. And then I apply this kind of self-supervised approach and fine-tune that for medical use cases. And then I can then have a task-specific prompting or fine-tuning, and then have some applications to geared towards consumer or could be geared towards the clinician. So that's a kind of overall recipe. Everybody's building on top of something, either a closed model like GPT-4 or Palm from Google, or they're taking some open source like Llama or Flamingo, etc., and then building on top of that model. So this is a common recipe that I've seen. The idea of the multimodal AI currently is to train encoders that convert a variety of inputs into the same space as the natural word token embeddings. From here, you can see that there's a structured data like age, sex, BMI, the lab values. What the first step is doing is kind of converting this data into like a sentence, so that it could be fit into like a natural language. And of course, if you interleave images, of course, the image will require, at least at this time, a different encoder to extract features, but then convert everything and then map everything back to a embedding space where image and text and video and everything has the same dimensionality that then can fit into a pre-trained language model. And then after that, it can go and create the output. So that's the kind of architecture that I have seen in a couple of latest papers that people implemented, that met Flamingo and met Palm, which is the latest one that came out from Google. Met Flamingo came from Harvard. So they have kind of used this very interleave type of data input, and then feeding that to a pre-trained language model. So what we did previously, before this ChatGPT era, we actually had this kind of very sequenced data, like data coming from lab, data coming from natural language and images, and we independently run through various encoders and then create the patient representations. And then we concatenated those patient representation and then feed into a let's say a deep learning classification model. So that's the kind of way we previously did all these things. But right now, because in the previous model there was no interactivity, and that is absolute must to have right now. And to take advantage of that, people are trying to see whether we can convert some of this embedding or encoding space into this kind of sequence model, so that we can take advantage of a lot of the pre-trained model that currently available. So what are some of the challenges you see in this realizing this vision? Of course, things are not that nice today, because the validation it requires a lot of diverse data sets, and currently those data sets may not be available to the people who are actually developing the models. And that's a lot of ideas around synthetic data comes into picture. A lot of the ideas around federated machine learning comes into picture, where you can access data from a variety of places and still validate the model. And then the second problem is verification, which is like an accuracy of the output, because a LLM type of model can have a new task. It can do a lot of new tasks, even that models are not trained on the task. But the idea of the challenge then comes is whether what the new task is actually is useful or accurate. So this is an ongoing problem that we kind of have to figure out as an industry how to solve. And then the third problem is the bias problem that we already have. I think the bias problem is related to the availability of data as well, that if you have diverse data sets, it's going to reduce some of the bias. And then, of course, privacy is a big challenge, but obviously that's a common challenge across the industry. But of healthcare, obviously, you don't want your EPHI to be leaked to inadvertently leaked to a model. And this cost is also consideration, because the large language model requires a lot of initial investment, but also requires a lot of investment into running. So that's also a consideration. So now what I'm going to quickly go through some of the have you seen that in order to create these models, we really need to understand medical data very carefully, because that's the way you're going to know how to validate things, how to create evaluation data sets, how to create training data sets. I'm going to quickly go through some of this, some of this concept behind medical data. The first thing is that when you're starting a project, there are some of the things that comes into picture that would be useful to know, like how to basically access the data. The accessing data is actually not that easy in healthcare, because you have to go through a lot of this process in order to get access. And then what modalities are actually you have available, and whether the modalities are linked together. Let's say you get an image, you get a lab test, whether I can link those two data together using a common ID. And this is a problem in the United States, because in the US, there is no unique medical ID. It's a kind of a hit and miss in many cases how to link those together. But in many countries, we have unique medical record, unique medical ID. Those countries like Canada and UK, it's a much less a problem, but this is a kind of a problem you see mostly in the United States. And then, how the real-time data be sent to the model, because of a lot of the legacy infrastructure in health systems, sometimes it's not easy to get the real-time data, and you require that in order to see some of the use cases that you have described. It actually requires a lot of the real-time data. And then how the data is pre-processed in real life, data just coming to model. If you do too much pre-processing, that's actually not good, because then you have to do that in an inference time, and then sometimes that's not practical. And then lastly, I would say that how might we connect to multiple sources? This is related to the access to the data, whether I can have a pipe to connect to the source systems like EHR, etc. Sometimes is a significant challenge. So now the second part of this is once you get access to the data, there are certain things you want to quickly figure out, whether that this concept of timestamp in healthcare is really important, and the shelf life. I'm going to describe it quickly what those things are. Like, let's say you get something from Fitbit from you, and you get Apple Watch, and then sometimes data could be sent every hour. Sometimes they could be sent every second or every couple of days. So depending on the time frame, your data might be a little bit different. So you have to understand those kind of sampling interval that you have. And also order of the events is important. Like, let's say somebody's having a diabetes, but before the diabetes, they might have other things like hypertension. So having those data in a sequence is really important, so that model can learn that somebody who has diabetes, who has hypertension, that person might end up in a diabetic condition. So those are the things important from the perspective of how disease conditions developed. And lastly, time scale. The time scale is whether you're talking about predicting for next hour. So let's say somebody has a sepsis condition, and I really want to predict what is going to happen in the next 30 minutes, compared to whether somebody will have diabetes. That's probably a long-term condition. So understanding this time scale is important from the perspective of the model. And then lastly, the life of data. We talk about big data, but sometimes this data might not be useful, because let's say data is 10-year-old and the people follow different medication practices that time, use a different procedure, then this data might not be useful. Then if you feed that data into your LLM, the LLM is going to learn a lot of unnecessary things and a lot of old things which might not be useful today. So these are the understanding the shelf life of the data, even if you have big data, is really important. Then the next thing is data quality. Data quality is really important for anything you do. But one of the things I would say that one of the thing that you have to worry about is the sources of bias and error, like how the data you have is actually going to have a good representation for the use case that you are developing. Let's say you're developing a diabetic model, and if you have data only for a particular population, it may not generalize well to the other types of population. So that's a kind of one of the biggest aspects of data quality. But the rest of the stuff is pretty similar to data quality that you handle in many other types of ML engagements. So data labeling is really important, especially even if LLMs are good at understanding the unlabeled data, working with unlabeled data. You really need data labeling for evaluation data sets. So be a consistent, having a tool that can help you model or label data across different modalities would be important, because you need to have consistency in terms of them. How let's say you look at image and you're saying somebody has a chest pain, and then you're looking at the natural language, it could have a similar thing that is noted there. So having some consistency across this data sets, and also this is going to help you actually do some data validation as well, whether you're seeing consistent things in natural language, in video, and in images. And this is one of the points that is really important. Why multimodal is really important is also this kind of data validation standpoint and data labeling standpoint. And lastly, data privacy and data de-identification. One of the basic stuff that is done in healthcare is to removal of 18 specific identifier, which are described in a United States law as a specific patient identifier that needs to be removed for HIPAA compliance. And also, this is not just applicable for structured data, but also applicable for unstructured data. In fact, removing PHI from unstructured data is one of the application of LLM. This is actually I used in a lot in using our NLP tool to do this kind of work. Rather than writing regular expression, you can do use your LLM to kind of remove some of this attributes. So that's pretty much it for the presentation. So I described the use cases and also described some of the some of the things, so the way the recipe is working for the multimodal AI. And lastly, I described some of the ways you could possibly work with your healthcare data. And this is the reference. I added all the reference here for latest papers from Google, from Harvard, and Microsoft, other places where you can look at how the multimodal AI, people are thinking about multimodal AI and how the experimentation is going on in this space in order to create some of the LLM aligned multimodal model.
Awesome. Thanks, Adrish. Thanks for going over such in-depth domain expertise on the different use cases, recipe, and tactical tips of dealing with medical AI and application multimodal. Would you be willing to share this slide on the
I'll share it with you
on the Zoom chat with the attendees, so they can follow up and then follow some of these references in further detail. In the meantime, so it's if the attendees have any question prior way, feel free to put it on the chat so Adrish can answer them asynchronously. And in the meantime, we'd love to have Jesse start unmute and sharing the screen whenever you're ready.
Yep.
Yeah.
Oh, hang on. I just need to update my preferences. My new Mac. Just give me 1 second.
No worries.
I'll just rejoin.
Yeah, no worries. Yeah, we have a couple of folks in our Discord community who's also pretty interested in multimodal in healthcare. So I'm sure that some of this advancement is very exciting for them to follow, right? Kind of curious, what does Rhino Health does? Adrish?
I'm sorry?
Your new venture with Rhino Health, what is
So Rhino Health, what Rhino Health does is it's a federated learning for healthcare. So it's basically helps connect to multiple hospital sites, or could be any other sites as well, and or make the data available for purposes of federated analytics or federated learning. So let's say you want to create a LLM and you want to validate your model with a diverse data set from multiple institutes. That's what we enable.
Perfect. Awesome. Also, Adrish, can you? I think you have to stop sharing the screen so that Jesse can pull the screen up. All right, I see it. Great.
Thank you.
All right, Jesse. The stage is yours.
Thanks. Yeah, you can hear me all right? Cool. Yeah, super excited to be presenting today, and I'm glad James reached out and find other like-minded multimodal interested people. I'm going to talk about multimodal vector search. And so this is certainly we're building an end-to-end multimodal vector search engine at Marqo. You can everything I show today is available at the GitHub. It's free, open source. And so I'll talk a lot about multimodal vector search and sort of go through sort of the entire stack. Just a little bit about me. So background in physics. I studied that for quite a long time, doing a lot of computational imaging, and then spent a number of years in the Bay Area and in Seattle working at Stitch Fix and Amazon doing robotics, and then founded Marqo a bit over a year ago to sort of bring a lot of the innovations in multimodal search to people. So what do we talk about? Multimodal vector search. So here's an example. Hopefully the animation is showing all right. But there's lots of different use cases, right? And I think we've already seen some earlier, but one is sort of this canonical use case for multimodal vector search is end user search. So maybe it's e-commerce. You've got a variety of data types. You've got images. Maybe you've got video. You've got text. And what this allows you to do is search it in the same way that you used to be able to search structured text data. And so you can have text-based queries, you can have image-based queries, you can have text-based documents, image-based documents, documents that comprise both images and text. And so it allows you to search across all of this unstructured data without any kind of necessarily having this really well curated structured data. And so you get these really, really powerful end user search experiences around e-commerce and product discovery and catalog search. There's also a lot of other use cases that we're seeing as well. So here's an example. It's might be a little bit hard to follow, but basically, augmenting ChatGPT with a multimodal, vector store, which is basically a multimodal memory. And so now, you can make ChatGPT, for example, understand images. And so this is a really sort of, I think early, time for this space and sort of seeing how it evolves. But certainly vector search and multimodal vector search, I think has a big place, particularly in the future of LLMs and around multimodal memory. So it's, I think, very exciting in terms of the sort of number of use cases that we're seeing. So now we'll go a bit of an outline on the talk. So we'll sort of just introduce a little bit about the basics of vector search and multimodal vector search, and then just sort of talk about what the system will look like if you're trying to actually do this, particularly for real-time vector search, which is something that we're really interested in. And then go into some more of the technical details. How do we get the vectors? How do we actually learn these representations? How do we adapt this for multimodal, and how can we actually kind of learn just beyond these representations and actually learn things like ratings and rankings as well. Right, what is vector search? So vector search is search using vectors. So this is a pretty uninformative description, but it's a relatively simple idea, and I think people will probably be familiar with this already. But the idea is that you've got queries and documents are represented by vectors, and the vectors that they get represented by in this vector space has this property that things that are sort of similar in their representations, that are similar in this vector space, are related in sort of concepts or relationships, and there's some meaning to how you actually want to sort of associate things. And so then what you can do is you can embed all of your documents, so turn your documents into vectors. Then when you turn your query into a vector, the whole search procedure becomes one of just finding the nearest neighbors. So it becomes this K&N problem. And so your query comes in, and then you calculate the distance or similarity with all of your documents. And then, the documents that are closest in this space are considered to be the most relevant. And so it becomes a very relevant, really, really simple operation of just finding the nearest neighbors. And so, the sort of success here really comes down to, how good your representations are and how good your learned vectors are at actually capturing these relationships that you care about. But one of the issues with this kind of naive method, although it's exact, it doesn't scale particularly well, as you sort of increase the number of documents in your index. So if you've got to calculate the distance with every single neighbor, it'll scale linearly with your index size. And so there's been a lot of innovation to make real-time vector search particularly much more performant by changing the problem from this exact K&N search in linear time to an approximate search where you can actually basically trade off some of your, sort of accuracy of finding the exact neighbors, but get a lot of time, benefits. And so now you can actually get much better scaling with your index size. And so it basically turns it from this kind of nearest neighbor lookup into this graph traversal problem. And one of the most popular ones is sort of HNSW, which I think, many people are probably familiar with. It's hierarchical, navigatable, small worlds. And so it's really nice, and, it turns it into this sort of, graph problem. You basically construct this graph you don't have this, every node connected to every other node. Instead, you do it in layers. And so you have long range connections. You go into a different layer, you have shorter range and gradually get shorter and shorter. And then when you're searching, you enter in at the top, you sort of do a greedy search with many candidates, you find the nearest point, and then you drop down a layer, you have new connections which are closer in proximity, you find until you can't find any more. And so this allows you to basically trade off your sort of accuracy for speed, which is a really nice trade-off, because sometimes you want more accurate, sometimes you want faster. And I think we'll see, there's a lot more innovation as well happening. So a lot of the time happens when you're actually just calculating distances between or similarities between vectors. And so we've seen some new methods really recently coming out where you can actually sort of do approximate distance functions for some of the candidates, and then dive into actual full distance calculations for more specific ones. And so this conveys quite a significant speed up as well. So I think we're going to see some really interesting traversal methods, particularly ones that combine learn methods as well, as we sort of speed this up. Okay, so we sort of just basically spoken about what is the sort of primitive operations of vector search. So how do we extend this, and sort of what is multimodal vector search? So again, multimodal vector search is vector search across different modalities. So typically, I think everyone thinks of vector search as sort of this semantic search, which is a text-based search, but really anything that you can turn into, anything that can be in a computer can basically be turned into a vector, and anything that can be turned into a vector can be searched. And so basically multimodal vector search is this generalization from just text into effectively every other modality. And so you can really now, have these incredibly powerful systems that, understand not just say structured data or text, but can actually understand, images, audio, depth maps, really anything that you want. It can be other things. It could be like job candidates. It could be profiles, really anything that you want to encode. And so the benefits are quite numerous. You can really learn these relationships, which will be very unique to your kind of use case, because maybe there's only particular modalities. It starts to put sort of search and recommendations coming together. If you don't have metadata, it means that you can still actually search things, and ultimately you get these really improved sort of search experiences. You get much more relevant content, and you can improve the business metrics. So we see better engagement, better add to cart, all this kind of stuff. All right, so we've sort of seen some of the primitive operations and what is sort of multimodal vector search, why we might want to do it. So now I'll sort of give an overview of what the sort of system will look like, because I think as well, we've seen that the vector databases as well, obviously been quite prominent recently, and we'll sort of show how to actually make vector search, you need something that's a little bit more than just a vector database and this kind of primitive operation. So here's a sort of overview of what the system would look like. And I'll sort of go through different pieces, and we'll talk about, some of these pieces as well in the rest of the talk. But there's really two main kind of pipelines that happens with, vector search. One is this kind of indexing phase, which is where we're turning all our documents into these vectors so that we can search over them. And then there's the search phase, which is where we have our query come in, and then we, compare it against all of our documents. And so in the indexing phase, what we do is, we start with basically, documents here, and documents mean sort of images. It could be text, it could be video. They come in, they get processed. So images, they'll be resized, there'll be some normalization, whatever needs to happen before it goes to the model. With text, we might break it up into chunks, might split it up by sentences or paragraphs. There might be some normalization, maybe some cleanup of the text, tokenization. Then this goes into the model, we get our vectors out. And so these are, effectively our embeddings. These represent, our documents. This gets stored along with the metadata, into a database, into a vector database, and can be used for searching. And then at search time, it's a very similar process, but now, our query will come in, it'll go through the same input processing pipeline. It goes through the inference pipeline again, and now we get a query vector. And so now we can actually start to compare that, like we saw before, against all of our documents that we've already previously stored. And then we can return a list of similar items based on their distance between, say, the query vector and all of our document vectors. And so that's sort of the primitive retrieval and ranking aspect that you can have. Oops. Okay, so that was sort of the system overview. And so now we'll talk a bit more about the actual vectors themselves. And so, this is sort of talking about this component of the system. So we'd sort of spoken about the retrieval and ranking and the storage component. So now we'll talk about, the inference and how we actually get the vectors. And there's lots of different ways, as we'll see. So yeah, vector search as well, and sort of this representation of documents, for example, as vectors has been around for a long time. There's also been, been many different incarnations of this. So TF-IDF and these kind of based methods have been around for a long time. They're considered to be sparse approaches because you're effectively got these really, really large vocabularies. So if you're tokenizing it, for example, it might be tens of thousands, hundreds of thousands in terms of the size, but most of these entries are going to be zero because you only have very few that you actually hit. And so these sparse approaches, been really, really popular. They've been, been incredibly robust, particularly around like zero shot. And so it's only been recently that they've really been surpassed by learned methods. And I think they're always going to have a place, particularly for exact match search. You're not going to beat that. And then there's been, more recent innovations like things like Splade, where you can actually, combine, these traditional sparse approaches with these sort of heuristics and actually combine them with like learned, neural networks, but for still doing it on a sparse approach. And then there's sort of this dense approach, which is kind of, coming straight out of a, a deep learning model, a neural network. And so this is using embedding layers, for example. And so this is much, much denser. So there's not really any zeros. You've effectively got, this kind of, full suite of numbers, but the dimension is much smaller. So looking at, hundreds to thousands, typically. And so, yeah, the models, are very flexible. You can have almost anything, turn it, something into a vector. But, we sort of, here's just an example of, say, multimodal one. Image can go in, you can get a vector out. Text can go in, you can get a vector out. And then you can sort of, index that and put that into your pipeline like we just saw. But really the kind of most interesting thing is actually how you actually learn these representations. And so this is was a seminal paper from OpenAI in start of 2021. I think a lot of people will be familiar with this. It underpins so many of these kind of modern multimodal methods, from generative AI to all of retrieval. It's just really everywhere. And so contrastive language image pre-training is what it was. It's an incredibly simple and elegant idea. It works really well, and it's really, really flexible, as we'll see. And so the basic idea to learn, what our vectors are is that we have, data sets of paired images and text. And so for each image, we have a caption, and we have many captions, we have many images. And so what you do is, for a batch, you'll have all of the captions. For a batch, you'll have all of the images. They go through their respective encoders. And then you've got a batch of vectors out for each of these. And what you're trying to do is it's a problem of predicting which caption goes with which image. So it's very, very simple. And so you're basically trying to, fit this identity matrix based on, your pairing of the captions and the images. You get this automatic kind of, in-batch negatives because you're saying everything that's off diagonal, everything that isn't the paired ones are going to be not paired. And so you don't actually have to necessarily even find, your own negatives. If you've got your own negatives, you can just append it to the matrix and you can add additional negatives if you want. It traditionally uses a softmax as well. So this kind of, if you're treating it like that, you'll actually have sort of two pieces of the loss function, which image, goes with which caption goes with which image, because you're going to be normalizing across different dimensions. And the key outcome of this is that you get this dual sort of embedding. So you can actually understand, images with language, you can understand language with images, images with images, language with language. And so they have this shared space. And that's really the most powerful kind of thing that comes out of this, is that you can actually train these encoders to effectively have this understanding of the different modalities. And this is really, really powerful and sort of enables, all of these multimodal use cases. And as we see, it's easy to extend this, to much more powerful sort of representations. And it's, it started out basically, I think most famous probably clip, but it's very easy to extend it to other modalities. There's no reason that you need to have images and text, really anything you can do. Anytime you've got an encoder, you can just use this loss function and you can get this kind of representation. So it's really, really, we're seeing it become just sort of a, de facto standard for a lot of the training because it's very easy to do, it's very easy to implement, and it works really well. All right, so now we'll sort of talk about, how we go to sort of extend that from just the sort of text and image to more complex multimodal representations, which we can use for multimodal vector search. And so this is sort of, talking about how we might actually represent, things in sort of this search system. So we sort of spoken a bit about the retrieval, the storage, the inference, the vectors. And so now we'll think about how do we actually kind of represent these, within inside the search system. And so here's an example of what I mean when I'm talking about multimodal representation. So here's just a sort of e-commerce example. You've got many, maybe you've got one image, maybe you've got 3 images, maybe you've got 10 images, maybe you've got an animation, maybe you've got some titles, some descriptions, some structured data. It could be any number of these. It might be, and it might be, the entire catalog might only have some of it. maybe it's got all of it. And so it's going to be quite different. Everything's going to have a sort of different representation. But the idea is that we can actually use any number of these images and text to represent an item. And so there's lots of different ways you can do it. There's really no hard and fast right way to do it, but it can afford, there's some really, really interesting ways of actually kind of representing it, and actually being able to, get a lot of flexibility in basically how you score, relevance, for example. So if you're using, different combinations of text and image, you can actually now calculate, this sort of aggregate, relevance of your query against all of these different components. And you can extend it to queries. It doesn't have to just be about the objects themselves, but you can have these kind of multimodal queries. And I'll show some examples shortly about what this actually means. And so, you can have this sort of, it doesn't have to be asymmetric. You can have multimodal queries, multimodal objects, and it becomes a very generic way to represent everything. And what this really allows, though, is a lot of also incorporation of like traditional search and IR techniques. So it allows you to do query expansion. You can have customized scoring. You can incorporate relevance feedback. It's effectively, you can start to have like ensembling. So you can actually basically exploit some of the properties of particular distance functions. You can effectively have ensembling at test time with almost, out incurring any additional overhead. If you can think about augmenting, as you index, you could do transformations to your data. And so it's effectively at scoring time, again, like a test time augmentation. So there's these ways that you can actually improve your kind of relevance, which are very well grounded in sort of other machine learning techniques. So here's an example now of what I mean with sort of the multimodal queries. So this one, hopefully you can see the animation. Searching for backpacks, and then it's cutting to an image. And so we're searching with both text and images across this. I'll wait for it to come back around. But basically here, the query is a text and an image. And so what we're doing is we're conditioning the search. So it's a search for text, which is backpack. And then we're conditioning it with an image. So here it's a colorful image. And so now we can actually get, basically colorful backpacks back. But what we can do is show the power of these representations. Is this second image is an image of the woods. And so not only do we now get conditioned search based on color, but we also get it based on concept. So we're getting backpacks back that are not just, equivalent in color, but functionally equivalent. So we're getting back hiking backpacks, which are green as well. And so it shows you the power, not just of having this ability to combine modalities, say for a query, so we can condition our text search based on an image, but it also shows that we can actually encode these other relationships just through, this representation learning. And so these become really, really powerful for, for creating these search experiences, and allows this kind of, per query personalization. And so this personalization can come from just about anywhere. Here's another example. We can do negation as well. And so this is, a lot of this stuff has been popularized, I think, particularly from the generative AI, particularly for text to image generation, where you have, additional kind of, I want to stay away from bad hands, for example, I think is one of the best examples. And you can do the same thing for search. Like there's no reason why you can't. And so here, we've searched for green shirt with short sleeves. And so what you get is, green shirt, button shirt with short sleeves. And so we say, hey, actually, we don't want to go near buttons as well. And so a green shirt with short sleeves that doesn't have buttons, we get back t-shirts. And so it becomes a really powerful way, again, to kind of, incorporate relevance. You can put these negative concepts into your documents, and you can actually curate these search experiences really well. And so here's another example, and it's, you can do it in natural language, which is also incredibly powerful. I think it lowers the barrier to entry. In this example, what we've actually got is I created some low resolution, blurry JPEG artifact versions of the images. And so it might be a little bit hard to see, but the ones that are denoted with a red square are actually the lower quality images. And so you sort of, in the negation bit, you just say, I want to stay away from low res, poor quality JPEG images, and now it suppresses, those particular ones. And so you can see how, through the actual representation learning, we can encode this kind of behavior. And so, now you can actually describe things in natural language, just like we've seen with, ChatGPT being so popular. If you can actually describe things in natural language, it can be a really powerful way. And so we can adapt, and like I said, with that sort of initial kind of, representation learning that I showed, where you've got the text and image from the original clip, we can actually adapt our training for multimodal vector search. And so, if we're doing an asymmetric kind of querying pattern where we've just got text, for example, but we've got this kind of multimodal representations, we can adapt our clip training, to actually reflect this and actually get better performance as well. And we can optimize it, based on the production setup, basically. You can use the same distance metrics as you're going to use in search. And you can update, for example, your query models without having to re-index any of your data. And so this is effectively, you can sort of remap your text, text encoder, as time goes on without having to re-index anything. So you can, actually swap out models very quickly. So finally, yeah, let's sort of talk about some learn ranking. So this is sort of a bit more kind of curation on the search side. So here's the previous, clip example where we have the, the text encoder and the image encoder, and we're trying to learn this diagonal. If we look at the, collaborative filtering, which is this canonical example in, recommendation systems, we can actually start to think, hey, this looks pretty familiar to what we've seen before. And so you can think about it, okay, now, instead of just the items and the users, for example, we've got our, text and captions and our images. And so, we can actually start to think about this as a recommender system problem as well. And so what we can actually do is we can not only do just what we did with learning the diagonal, we can actually incorporate like list-wise optimizations. And so if we've got a ground truth ranking, we can actually start to learn that as part of this training. If we've got ratings, so we don't even need just a relationship, we can actually have a magnitude, a rating, we can also incorporate that. And so here we're able to not just have relationships, we can have rankings and we can have ratings as well, all part of our representation learning. Here's an example of just how you can actually use this to then curate and personalize basically the search results. And so here we maybe it's someone's liked items, maybe it's a ranked list from top selling. You can actually even start to think about cloning search results from other websites if you really want to. And so yeah, you can curate this is backpack again. You can curate these search results based on additional context, additional metadata. You can learn this kind of ranking as well. And so it becomes really flexible in how you actually can do everything and actually curate this search. So that's the end. So thank you very much. Yeah, GitHub, check it out. Blog as well. We've got lots of interaction with generative AI. We didn't speak too much about that today. And we're also, hiring a principal applied scientist. So if anyone's interested, contact me. Thanks.
Awesome. Yeah, thanks, Jesse, for that very in-depth walkthrough from the initial units of vector and vector search to this concept multimodal vector search, and then that sort of demonstration of I think that demonstration contrastive learning and that vector map in the multimodal space is really cool, right? Because now you can to your point, do negation, do addition, with like not just numbers, but like not just text, but also like images, right? So I think like as just I guess like partition models become even more powerful, we can like do this sort of arithmetic, right, in the later space to be even more performance and faster, right? I'm curious, audience, if you have any question, feel free to unmute yourself and ask right away. But yeah, I guess like I'm curious, Jesse, like what do you think regarding the adoption of multimodal search, right? Like what do you think is gonna take to like for the application to be even more widespread, right? Compared, like these seems like very awesome demo, but what does it take to like get them to be even more scalable in production? Like like let's say in healthcare system, right? Like what Adrish talked about in some of the research paper. Yeah, what can help bridge the gap between prototype and production?
Yeah, I think a lot of the heavy lifting has to go into the machine learning models, and so the barrier to entry to make it work well is still quite high. It's it still takes quite a lot of effort, right? Like a lot of domain expertise. I think the vector database and the similarity is kind of being commoditized, and we can do that. That's fine, but to actually make good search with vector search still requires quite a lot of effort. And so that's what I think we're trying to work on a lot on the modeling side, because there's a lot you can just do. I mean, it's not just like one, it won't be one solution, but if you can make that the sort of just, train a model that's domain specific based on whatever data you have, just super easy, then you've already got like in a really good place. And then there's sort of like I mentioned with the representations, after you've trained the model, you can adjust kind of things, to actually get the results right. And so what we're seeing is just, trying to basically, systematize a lot of this process so that people can just, do it at the click of a button basically. And so, we've seen, this has really been driven from a lot of, work with customers, particularly at scale, trying to, around like e-commerce and product search, actually, getting above, particularly the keyword search, for example, because there's a lot of places as well, a lot of marketplaces, aggregations where they're using user generated tags and things like that, which can be really noisy, inconsistent, and so actually being able to do it without relying on that is we've seen as being really compelling and can really improve search. But yeah, basically I think we're just going to lower the barrier to entry, and so make it really easy to get really high quality models and then give people the tools to adjust search after they've trained the model.
Yeah, that make a lot of sense. Especially with that, I think on your slide on recommended system, when you have that line which